Hello students, and welcome to your lecture on the structure of Earth and plate tectonics. We're not going to be reading the book on this section, and so this will be your only introduction to plate tectonics except for the activity we're doing in class. So the structure of the Earth, you have to realize that the Earth is actually organized by density. So with the least dense, the atmosphere is on top, and that's made out of gases. And then you have the ocean, which is made out of water. And then there's two different types of crust. The continental crust is less dense than the oceanic crust, and that's based on the types of minerals you find in those rocks. And then as you go down into the mantle, you have the asthenosphere, which is partially molten and made out of a slightly less dense minerals than the deeper mantle. And then when you go down to the core, it's largely made out of liquid iron and nickel for the outer core. And then because of the extreme pressure, solid iron and nickel in the inner core. When you look at the layers, there's two different references you often hear. You'll hear, crust, mantle, core, but you'll also hear these terms called lithosphere and asthenosphere. And the layers are slightly different. One is based on the composition when I talked about minerals on the last slide. The other one is based on mechanical layers, meaning how rigid or how plastic or flowable are those layers. And when you think about the plates and plate tectonics, you often hear people refer to it's made up of the crust. It's actually made up of the lithosphere, which is the crust and the upper solid non-plastic part of the mantle. And then as you go down into the core, another really important facet of planet Earth is that we have this liquid outer core, which convects. And that convection actually drives our magnetic field. And our magnetic field is more important than you might think. It's more than just making our compasses work. And it's actually a little different than our geographic North Pole, and it wanders over time. But, and actually every once in a while it flips, and it doesn't flip on any kind of periodic basis. It's hard to know. They seem rather random in points in time. And we can record this through ocean rocks, rocks on the ocean floor. We can see those bands of magnetic reversals. But why is it so important to us? It actually would be hard to have life on planet Earth without our magnetic field. The sun puts out the solar wind with all these ionizing particles, and our magnetic field basically directs most of that right around the Earth, which protects us. Without our magnetic field, we would not have an atmosphere, or our atmosphere would get stripped away. And we can see this because it's what's happening to Mars. So heat flow within the Earth. What are those heat sources? The latent heat from the formation of the Earth. That's basically when the Earth collapsed into a planet. There was a lot of compression and pressure, and that rose, made temperatures go up, and we still have a lot of that left over because the Earth is a decent sized planet, unlike Mars, which is a much smaller planet and had its core basically freeze a while ago. We also have a lot of radioactive elements in there, which put off their own heat. So the temperature inside our Earth is extremely hot, and we're in a cold space, and so the Earth is going to constantly try to cool itself off, and it does that through convection, both convection in the core and convection in the mantle. And then the crust of the Earth, the lithosphere itself, is cracked, and where you get those plates, the heat can escape, and we have things like volcanoes. So it's kind of a very simple view of what's going on, but it gives you the general idea. How do we know what's inside there? It's actually not as straightforward as you might think. So first off, earthquake waves. When they travel through the Earth, we've got two different types, the P waves, which are faster and they can travel through anything. And then we also have S waves, which are slower and they can't travel through liquids. So we'll have shadow areas. If there's an earthquake somewhere on Earth, and if those waves, if they're forced to travel through our outer core, the S waves can't make it through. And their speed is going to be dependent on the density of the material, so we can get an idea of the density of various layers within the Earth. What are some of the other pieces of evidence for what's inside the Earth? Well, volcanoes erupt, and they erupt places like Hawaii, erupt from fairly deep in the mantle, but they only erupt from the mantle. We've never had a volcano erupt liquid iron and nickel from the core. That would be cool, but it doesn't happen. So how do we know what's down there? We also, through the motion of plates on Earth, we can get a sense from what's underneath, because different areas will erupt different places from within the mantle. And we can get a sense for those convection currents. And we can actually do some imaging now too to look at the downgoing plates. But that's all fairly shallow. For the core itself, it's really kind of bizarre, but we think it's made out of iron and nickel because we get meteorites from the asteroid belt where there was another planetary body at some point. And we have two types. We have the rocky meteorites that they look a lot like rocks from our mantle. And we have metallic meteorites that are made out of, guess what? Iron and nickel. So it's a little bit obscure, but iron and nickel are also not that rare. So if we're going to have a metallic core, we know the iron because of the magnetic field, but we also, the nickel part, it comes from looking at these metallic meteorites. Okay, so you've seen this map, the plate tectonic map of Earth. Plates can be all different sizes. Off our coast, we have a fairly small one, the Juan de Fuca plate, but we also have some fairly large ones like the Pacific plate, the Eurasian plate, and the North American plate. And how do we figure out where these plates are? We can see things like volcanoes and earthquakes, and they tend to form along these bands. And different types of plate boundaries will have different types, of earthquakes and volcanoes. The Ring of Fire is the most famous one, and it's the one that surrounds the Pacific plate. And we have the really huge potential for really huge earthquakes, and also the really tall, pointy volcanoes and fairly active volcanoes. So the Ring of Fire is actually made up of mostly converging plate boundaries. All right, so again, we talked about this a little bit, but what drives it? So that heat escaping from the core is trying to get out. Convection currents are the most efficient way to do that. They're not as neat as these nice little circles you see in the diagram. They're much more complex than that, but it gives you the general idea. So where those currents rise, you're going to get the plates pulled apart and you're going to get divergence. Where they sink, you're going to get the plates coming together, and that's called convergence. And where they sink, you generally have some of that crust dragged down with it, and you get something called subduction of part of that plate. And I'll call it crust, but really it's lithosphere. It's just that is a mouthful. So people tend to fall back on the word crust. And you can explain most major features on planet Earth with these motions. So we're going to walk through them one by one. We have the first two boundaries already mentioned on the last slide, the divergent boundaries and the convergent boundaries. But there's one more type of boundaries that we live on a spherical Earth. And in order for things to fit, you're also going to have places where the plates slide past each other. And we call those transform boundaries. And then finally, this is not a boundary, so it's a little bit of a misnomer on this slide. But hotspots are places where we get massive amounts of volcanism, like Hawaii is a hotspot, Iceland is a hotspot, Yellowstone is a hotspot. They're right in the middle of plates, and their origin and how we think they're formed is a little bit different than regular convection and plate tectonics. So we're going to step through these one by one. Divergent plate boundaries is where the plates, just like it sounds, are pulled apart from one another. And so you get rising magma from beneath, forces its way up, and it kind of forces those plates apart. What you get is always oceanic crust. You don't get continental crust coming out of divergent plate boundaries. So the eruptions, ocean crust is made out of mostly basaltic material, and that's non-explosive types of eruptions. Basalt is very liquidy and it runs really well, and it doesn't tend to build up and explode the way like our Cascade volcanoes do. But you do get an undersea mountain chain, both from all that lava coming out that does build up over time, but also because of all that heat coming up from beneath, it kind of bows the lithosphere up and makes it rise. In the middle of that, you're going to have a rift valley. So as it pulls apart then and where that basalt comes out, you're going to have a valley in the middle of that mid-Atlantic or mid-ocean ridge, and the mid-Atlantic ridge being our most famous one. So what does it do? If you already have an ocean, it's going to make it bigger, but it can also create new oceans if it's ripping apart a continent. And the best example of that is the Great Rift Valley in Africa. And here's a picture of that. There's actually what they call a triple junction here. These have already opened up, and then these are the Red Sea will eventually be the Red Ocean. We have this Gulf right here. And this third part, the third arm of what we call that triple junction, the Great Rift Valley in Africa, you can see the rifts here, and there's a lot of volcanism there. Eventually that will open up too, the sea will flood it, and it will it'll look a lot more like the Red Sea does today. So this is interesting that you can actually take a continent and rip it apart. And over the course of time, we've had various supercontinents in the past, like Pangaea. They have been broken apart through this process of divergence. The other thing that's worth mentioning is that at these divergent plate boundaries, and this is a slide that came from my thesis advisor, you also get a lot of circulation because most of these are going to be under the ocean. You get a lot of circulation of hydrothermal fluids, and what those fluids do is they're super hot. and they tend to leach certain minerals, and what comes out of those are metals. And so there's also a whole life, the hydrothermal vents, that hosts all kinds of life on the ocean floor. But since we're focusing on geology for this lecture, what I want to mention is that when you leach those metals with those super hot fluids, and we're talking like 300 to 400 degrees Celsius, they're going to get deposited then where those fluids come out, and generally in the form of sulfides. But a lot of our metallic ore deposits on planet Earth, you're going to go look for those hydrothermal deposits, not just under the ocean, but maybe places that used to be in the ocean, but also in places like Yellowstone, where anywhere you get a lot of hydrothermal activity, you can also get metal deposits. So I have a few examples down there in the bottom. And again, we have sulfur is a fairly common element on planet Earth, and a lot of our metals occur naturally, not as pure metals like the way gold does. Gold's kind of an exception. A lot of our metals occur as sulfides. So one of the problems we'll be looking at later in our air pollution unit is that, say, in order to get the copper and zinc out of the copper and zinc sulfide, you have to remove the sulfur. And traditionally, we've done that through a process called smelting, which then blasts that sulfur up into the atmosphere, which can lead to things like sulfuric acid and acid rain. So let's move on to convergent plate boundaries. This is where the convection currents are sinking, and so the plates are dragged together. Usually the one that gets subducted or goes underneath the other one is the one that's going to be thinner and denser. So if there's an oceanic plate involved, that's going to be that one rather than the continental plate, which is thicker and less dense. And if you got two ocean plates, it's generally the older and therefore denser ocean plate that goes down. The one that goes down eventually gets partially melted along with all the sediments and whatnot that was on top of it, and you get explosive volcanoes. And we'll talk about a little bit about why those volcanoes are explosive in a future slide. The other thing that happens as you warp that crust down, remember, it doesn't just bend easily. So as you warp it down, you get a big trench as it bends down. And so off the coast of our Oregon and Washington, we have a trench. There are three types. You can run two oceans together. You can run an ocean plate and a continental plate together, and you can run two continents together. So we're going to step through those because each one leads to slightly different features. And all of them actually come with the possibility for very large earthquakes. So where are they? I already mentioned the Ring of Fire, but you can see it's a little complicated over here. We have a bunch of convergence zones. Those little pink triangles these are all the convergence zones. We also have one here. And this is why the Alps are there, and this is why the Himalayas are where they are. So let's talk about the three types. When you have two oceans that come together, again, the older, colder, denser one goes down, and you get that deep trench. So up on the surface, you get something called an island arc, and it gets that name because the actual shape of these island chains are often arc-shaped, and we won't go into the mechanics of why, but just realize when you see an arc-shaped group of volcanic islands, you're looking at a subduction zone. Generally, all of the islands in that island arc will be around the same age. All of the volcanoes will be active, and you're going to get those big pointy explosive volcanoes because as you bring one of the plates down, like right here, all of the sediment that was on top of that plate that's been deposited in the ocean, that's water-rich sediment. It's been at the bottom of an ocean, and it tends to drive melting down here. And as that upper part of the plate melts, it then becomes more buoyant, comes out in the form of volcanoes. So we have quite a few of these on planet Earth. Some examples at the bottom are the Aleutians. One of the ones that's not on the map on the next page is the Caribbean. Think about it, very nice arc-shaped set of islands, all volcanoes like Martinique. And but if you look around the Ring of Fire, we have the Aleutian arc, the Kurile arc, the Japan arc, all of these arcs. They're all arc-shaped strings of volcanic islands, and that's all because of the Ring of Fire. Those are all convergent boundaries that lead to those subduction zones. And again, in all of these places, you're going to, because it's volcanic, you're going to get those hydrothermal deposits through circulation of hydrothermal fluids. All right, so what if you run an ocean plate into a continental plate? This one's pretty straightforward. The ocean plate definitely is going to be the one that goes down because it's older and denser. And as it goes down again, it drags down those sediments with it. So same process that you get with the ocean. But instead of an island arc, you get a chain of volcanoes on the continental plate. And as it melts, it'll often melt some of the continent too. So you're launching out some of the original material that was on the continent as well as those sediments. And those sediments probably came from erosion of the continents. And that's why you have a different composition, that less, not so much basaltic, but you get the more granitic material, more silica-rich lavas coming out. They're also going to be, if you look at our Cascade volcanoes, they're all also mostly the same age. And some of them are more active than others, but at any time, any one of them could become active again. We also get a trench off the coast for these types of collision boundaries. All right, so this is just a picture of our little Pacific Northwest from Mount Baker all the way down into the Northern California, Mount Shasta, Mount Lawson, and in other places, the Andes in South America. And again, you're going to get lots of hydrothermal deposits and so potential mineral metals that will be rich in this area. So a lot of mining prospecting goes on out here. So about that explosivity thing. So viscosity, how runny or how thick and goopy a lava, a magma is going to be one of those things that drives that. And that is driven by the chemical composition. I mentioned the word silica, which is like if it was a rock, it would be called quartz. But if a lot of silicate minerals are the most common types of minerals on planet Earth. And the more you have, the more thick and viscous your lava is going to be. And silica itself, you think of quartz, it's light in color. And so you can recognize rocks that might have been from a more explosive volcano if they're not dark black the way basaltic magmas tend to be. So the other thing that's going to drive it is temperature. The hotter it is, the more fluid or runny it's going to be. The other thing that's going to affect the viscosity is how much gas do you have. So when you subduct these plates that have lots of water-rich sediment sitting on top, you're going to have more gases in there. And as that plate melts, those gases are going to get mobilized and you can make your volcano much more explosive. So when you look at basaltic magmas in places like Hawaii, and think Mauna Loa, they're not very pointy. And sometimes they're even hard to recognize as a volcano from a distance because they just look like a big mound. So low viscous magmas like basaltic magmas are going to flow along distances versus your more viscous high silica magmas are going to make these, not only will it explode, but the lava itself is way more goopy. So it just doesn't flow very far. So it tends to pile itself up on these big, nice pointy volcanoes. And then, you think, well, what about the Olympic Mountains? We have this whole mountain range sitting right out. And it turns out this is kind of a side note, but they're really rare on planet Earth. When I talked about dragging all those sediments down, well, what if you have so much sediment sitting on top of your plate that it can't all get dragged down? It tends to get all scrunched up at that boundary where the plate goes down. And so these would be ocean floor sediments that get squeezed up and anyway, so what causes that? Well, if you have lots and lots of sediment, what causes lots and lots of sediment? A super big river. So we have our Columbia River and those sediments, Oregon doesn't have Olympic Mountains because those sediments, the currents off our shore tend to drag those sediments north. If you look at the ocean shores, look at the shape of that spit or down in Aberdeen, things get dragged to the north. And so as all those sediments sit on the Pacific plate or the Juan de Fuca plate that's going underneath the North American plate, they build up and they can't all go down, so they get scrunched up, and that's the Olympic Mountains. Not volcanoes. The Olympic Mountains do have no volcanoes in them, but if you look at the rocks closely, they're scrunched up sediments. Where else does this happen? Barbados. If you look at, here's the Caribbean arc, these are all volcanoes. Barbados is not. It sits out in front. This plate's going underneath this plate over here. So the Atlantic Ocean is going underneath the Caribbean there, and or the plates that are there. And Barbados is an accretionary wedge. It's an island though, because this is two ocean plates meeting. So I find this really fascinating, but it is really rare on planet Earth. So what if you run a continent into a continent? Generally one tries to subduct, especially if it was attached to an ocean that did go down. But generally a continental crust is too thick to subduct. And so it might partially go under, but then it just literally gets bogged down. And so instead of going down, things go up. So our tallest mountains on planet Earth are going to be where you run a continent into a continent. And so right now, the Himalayas, India, rammed into Asia, and it's still actually ramming into Asia, and the Himalayas are still rising. So because you don't have a plate going down, there's no volcanoes, but you can get some big earthquakes, and you get, again, just super tall mountains. And so the Appalachians are an ancient example of this. The Alps are another example. So right now there is still what was the Mediterranean Ocean is still going down, and you get those volcanoes in Italy, but the Alps themselves are not volcanic. So what about the third one, the transform boundary? We live on a spherical Earth, and it turns out in order to make things all kind of fit, all this motion, you can't just have things going down and things going up. That's kind of more of a two-dimensional world. We have a three-dimensional world, and between transform faults, between mid-ocean ridges or those divergent plate boundaries, we tend to get these transform faults, and that's places where the plates slide past each other. So usually this occurs between different areas of the divergent plate boundaries and mid-ocean ridges. And you're not going to get volcanoes because nothing's going down, nothing's melting, but you do get earthquakes, and sometimes fairly big earthquakes. Not as big, you know, your convergent boundaries, you have all that pressure building up, you can get up to the size 9 earthquakes, but at transform boundaries, you can get up to size 8 earthquakes. So examples, you guys all know about the San Andreas, but also Haiti and the South Island of New Zealand are 2 more. And these are land examples. Nearly all of our transform faults are underneath the ocean, so we don't really think about them too much, but these are the ones that have actually are above land. So here, so why do we have this one above land? We actually have a mid-ocean ridge right here that's splitting off Baja, Mexico from the rest of Mexico. And then we have another mid-ocean ridge here. And in between those two, we have a really long, it's one of the longest out there, transform fault called the San Andreas. And so it runs all the way, it goes offshore north of San Francisco, but then it goes more inshore east of Los Angeles. And so here it is, the Bay Area along highway, I think it's 280. There's this reservoir. This is the San Andreas Fault. It tends as that those plates rub, they tend to erode the rock. And so you get these valleys. And here it is in Southern California where it's much more dry. Okay, and then the final one is hotspots. They're not located at plate boundaries. You have a deep source from deep within the mantle. We can tell this through things like isotopes and the kinds of lavas that erupt out of hotspots. If you go to Hawaii, the Big Island, like Green Sand Beach, those olivine-rich lavas are deep ocean or deep mantle lavas. And so anyway, when you get them underneath an oceanic plate, you get these nice chains of volcanic islands like Hawaii, like the Maldives. And they're very different than island arcs. They tend not to be arc-shaped, but they also are very different in age. You have the one that's active, which is where the hotspot is right now. And as you move away from the hotspot, things that are older, so as the plate slides, the islands that are further from where it's currently active are going to get older and older. So if you look at Hawaii, Kauai is the oldest island. It's been a long time since Kauai's erupted. The Big Island, as you know, is still active today, but it is actually starting to slide off the hotspot, and there's a new island forming that hasn't reached the surface of the Pacific Ocean yet, and they've already named it Luihi. But if you look, it goes way beyond Hawaii. And here's a place where at that point in time, the direction of the plates must have shifted because it takes a kink and eventually subducts underneath the Kamchatka Peninsula. And here's the Aleutian Arc there. So these are fascinating. And again, we don't understand them super well. It seems like they're not really affected by the convecting currents in the upper mantle asthenosphere, and it must be a hugely voluminous amount of magma to come up like that, keep erupting for decades and generations and be so active. And it's a lot of material. And so we think they're maybe caused by hot spots on the core that melt the mantle right above it. That's always basalt, and the explosions are not super explosive, at least when they come through ocean plates. And you get these big, wide, low viscosity, so big, wide mountains like Mauna Loa, which is as tall as Mount Rainier, but looks really different. But what happens if you blast them up underneath continents? Then you can get really explosive, big explosions, because you have to melt that continental crust in order to blast your way through it. So Yellowstone is an example of this. Also the Deccan traps in India. Not sure if you can see it up here in the corner with my little picture, but you can melt an awful lot of continental crust if you have an awful lot of stuff coming up from underneath. So the Deccan traps are about the same age as the dinosaur extinction 65 million years ago. And so that's some people propose that was one of the causes of the dinosaur extinctions, was that extremely voluminous amount of lava coming up. Of course, we know that there's a meteorite impact now. But if you look at Yellowstone, and here's a map, this is where the hotspot is now. And as the Pacific plate moves this way, these are older areas where the Yellowstone hotspot used to be. And it goes right across the state of Idaho. And again, they can cause super, super massive explosions that can leave a caldera behind. So the hotspot itself doesn't move, it's the plates above it that do. So this is kind of cool. And if you look at the ages, this is where we are right now. And then the oldest ones are furthest away. If you look at the ages here, where the hotspot is right now is right there. Looking back at Yellowstone, this is just a map. You may not realize this, but here's where it's really hard to tell that Yellowstone is a caldera because there's been lots of later, smaller eruptions that have kind of filled in that caldera. But look at it blasted. This is Idaho. Though that valley in Idaho is a series of calderas that literally blasted a hole through the Rocky Mountains. Really striking when you see it on a satellite map or like a representational map like this one. All right, surface geologic processes. I'm not as excited because it's way more slow process, a little bit more boring in my mind, is that you're going to break down those mountains over time through processes of erosion, which are driven by wind and water. So the physical and chemical processes that break things down, you can call it erosion, you can call it the weathering of rocks. And this is what's going to develop our soils, which will be the topic of our next lecture. And water is probably the biggest source that's going to erode, but wind also plays a role. And then just a little bit on rock types. You're going to have 3 types. Your igneous, which when you think volcanic rocks, those are the ones that come where the magma launches out. And when magma reaches the surface and comes out, you call it lava. And then those, because they come out and they cool quickly, you tend to get rocks with small crystals. You can even get glass if it cools super quickly. But then there's also the magmas that never make it out, and they slowly cool in the crust itself. And because they cool slowly, you get those nice big crystals that if you have a granite countertop, that magma cooled underground. Then there's metamorphic rock. If you really put a rock under a lot of heat and pressure, it can flow, even though it's rock, and it doesn't really flow like a liquid, but it can get warped and distorted, and you can get different minerals forming. So often this is caused by burial and proximity to volcanic areas. And the most common place that you're going to find these are in convergence zones. So all that pressure is going to cause that rock to get distorted. They tend to be very dense because they've been crunched together, and often you can get minerals that will rearrange. Garnets are metamorphic, and they form from things a lot less dense like feldspars. And they're a lot of our gemstones come from, sorry, the cat is disturbing the lecture. a lot of our gemstones, because they're nice and dense, we want them to be durable, come from metamorphic rocks like diamonds, sapphires, and rubies. All right, and the final one, sediments. If you take that dirt and you compress it over time and make it into rock, you can make a sediment. We classify those on particle size, from shale, which is like taking clay and making it into rock, all the way up to conglomerates, which is like taking pebbles and making it into rock. Breccia just means it's like jagged rather than rounded. So if you're going to find fossils, generally you're going to find them in sedimentary rocks because the animals die and they get buried in sediment and eventually can become rock. So here's a little picture of a trilobite, long extinct. We find them anywhere. They were really common. So you find them, I've found a few in New York State. You find them all over the place, but they're buried in sediments. All right, and then finally the rock cycle. It's not really a cycle, a little bit of a misnomer. It just means that any rock can become any other rock. You can take a metamorphic rock, throw it in a volcano and melt it, and now it's an igneous rock. You can take a sedimentary rock sitting on the ocean floor, subduct it, melt it, now it's an igneous rock. So you can also take any of those rocks, crunch them, make them metamorphic rocks, and you can take any rock and break it down so that then it's a sedimentary rock. So I hope you've enjoyed our little geology lecture for the day, and make sure that you let the lecture run out before you exit the Ed puzzle.